Alright, so welcome back to particle physics and the Standard Model. This is lecture 55, and last time we finished our discussion on decays, and in particular we did finally see why the dimensionality of time, there being only one dimension of time, is intimately related to the fact that only heavier particles can decay to lighter particles and not the other way around, right. If you had more than one dimension of time, then this would not be true. Okay, so we should be thankful we are in a world where there is 3 space dimensions and one time dimension. And then we started doing some scattering calculations without really invoking QFT, right. And in particular we were computing the we are seeking to compute the cross section of this process, where the energies of the initial and final states are so large that you can neglect the masses of the electrons and muons. Okay, but also we are considering this process at sufficiently low energies that we don't have to think about the Z boson in this process. Okay, only the gamma, only the photon is doing the mediation. This is a QED process. Okay, and where were we last time? So we wrote down, first we wrote the amplitude for this process in terms of another rescaled amplitude, where I pulled out the coupling constant squared, right, and I was able to reduce the problem to one of spins or helicities. Remember? Right, the propagators and the spinor currents all cancelled in the numerator and denominator, and then I reduced the problem to just computing this, and this is now nothing but switching labels again a bit. If I take the inner product of, so I am calling this 1, 2, 3 and 4 both spin labels and momentum labels. So I am taking the inner product with what exactly? The polarization of the photon. Yes, and then I picked P1 and P2 to lie along the Z direction, right, so that the momenta were basically this, right, and P2 is this, correct. So these are the variables with which we are going to work, and I ended last lecture by looking at some possibilities for the S1 S2 state. Okay, and I said that these could possibly be like this, or like this, or like this, or like this. What does this mean? So the polarization, or in this case the helicity, could be in the x direction, or it could be in the y direction. Now where y is now coming out of the board, okay, coming out of this plane. Okay, so I cannot draw it that way, that's why I am drawing it with this horizontal double arrow. Alright, it has to be, right, because the propagation is in the z direction. Okay, now not all of these could actually participate in the scattering process. Okay, why is that? Because only the possibilities of the helicities that add up to a spin 1 can participate in the process. Why? Because you are connecting to a photon here, right, you have to go through a photon, right. So even though this is not in real space, the Feynman diagram all in momentum space, the point still stands. You have to go through a photon, so you can only pick the possibilities that give you the correct polarization. Okay, so let us write that down. in more detail, this possibility for S1, S2 produces, what can it produce? This is in the y direction, right? Or I can call this the x direction, right? So whatever it is, I can produce a photon of a polarization given by this vector. Okay. And this produces another polarization. Sorry, this is 0. Okay, this is what we call y now. Another polarization in this vector. Correct? Because if I have this and this, they're not going to add up to 1. The spins are not going to add up to 1, and I'm not going to get the correct polarization for the photon. Okay. Okay. That's the initial state. All right. What about the final state? Okay. How can you think of this for the final state? So I have accounted for this. Okay. So I have accounted for this particular term now. I've taken S1, S2, and then I know that I get these two polarizations. Okay. But I should still do this, right? The final state also, the final state polarization also I should care about. Correct? Now, to get that bit, this inner product, we have to consider the final state momenta first. And from there, you can think about the final state helicities and think of the final state polarizations. Right? So, let's now draw this process in real space. This is not a Feynman diagram now. Okay. What have I done here? This is the electron and the positron and the final state also, of course. Okay, so this picture is intuitive, right? This, what I'm drawing as horizontal lines, that's the initial state, and then they crash and produce the mu1 and anti-mu1. Okay, so to give the momentum labels, this is P1, P2, P3, P4. Okay, and most importantly, this is in the center of momentum frame. I'm literally drawing this in the center of momentum frame. That matters now because I'm thinking of this scattering angle, which I call theta. This angle is in the center of momentum frame. Okay, in another frame, this angle obviously will change. Okay. So now we can easily write down, now that this is the picture, right? It's now trivial to write down what P3 and P4 are. So just like over here we wrote this, right? What is P3? Mu. I'll have the energy out. I have 0. Now this is the xy plane still, right? So I have sine theta, cos theta. Okay, is that clear? It's just trigonometry, right? Not only that, I've also used energy momentum conservation, right? So you can easily work this out, how energy and momentum conservation are used here, especially after I write out P4, which is nothing but minus sine theta here and minus cos theta here. So clearly if I add P3 and P4, I get P1 plus P2, right? And similarly, separately if I conserve energy and momentum also, I'm going to get this. Okay, it's a simple collision problem. Okay, of course, I have assumed azimuthal symmetry here. Okay, I did not specify what is the phi in this problem. Okay, so I cannot easily show this on a two-dimensional plane, but by azimuthal symmetry you can understand what I mean, right? So this so the mu plus and mu minus in cylindrical coordinates could have gone off in any azimuthal direction. It's just that for this particular problem I'm assuming that phi equals 0. That's why I'm drawing it on this very plane. Okay. Okay, good. Then we can then ask, in the final state, okay, what could be the polarizations of the photon? Okay, one possibility is clearly this, right? How do I know that? Let's go up here. Look at this, it's 1, 0, some non-zero number, some non-zero number, right? That's the momentum. So the photon polarization, and I'm not talking about the polarization of the photon here. Okay, so one of them is clearly this possibility, because this is orthogonal to the P3 and the P4, right? But what else? What is not so trivial to see is that this is yet another possibility. Okay, what does this mean? In this case, it means it is coming out of the plane, right? So if the muons are, flying literally on the plane of this device, then so you can see the way I'm holding the pen, right? It's now coming out of the plane. Okay, the polarization is orthogonal to the propagation and coming out of the plane. Okay, so let me try to draw it on this. So all this means is this is one direction of the polarization and the other one is out of the plane, which we draw like this. Okay, so this is 1 and this is 2. Okay, so if you want, I can draw more such dots to show the direction of polarization. Okay, so these are the polarizations of the photon that we need to hit with. Okay, and for completeness sake, let me just write this. All I have done is identify the polarizations using the polarization condition, that it has to be orthogonal to the direction of propagation. Okay, all right. So now we can very easily solve this problem now. Why? Because we have the polarization vectors of the initial state, polarization of the final state that you need to hit, right? Because we identified the photon polarization there, and we just need to take the inner product and sum over it. Okay, so we are going to do that, sum over possibilities is that let's call it M1, which is the first possibility, literally that I take this as my electron state going to mu plus mu minus state. Okay, and what am I doing now? I have to okay, yeah, okay, I can write it this way, no problem. So okay, you see what I've done here? So this epsilon 1 corresponds to particularly this helicity states for the electron, right? That's how we derived it up here, right? Right, this is particularly what corresponds to epsilon 1, but I have to sum over all the spins that the muons can take. Okay, why? Because generically muon spins are not measured. Okay, and that's exactly why you have to sum over the possibilities of the muon spin in the final state. And that's exactly why I have to put in both epsilon bar 1 and epsilon bar 2, where bar stands for the final state. Okay, so I take this initial state, that's epsilon 1, I have to hit it with both spin possibilities which we have derived here. Okay. Okay, now what is, so this is a 4 momentum dot product, if you will. Okay, 4 vector dot product. So what do you get now if I do that? Take epsilon 1 and epsilon bar 1. So here is epsilon 1, 0, 1, 0, 0. Epsilon bar 1 is also 0, 1, 0, 0. So the first term is 1, right? But it's not just 1, it's actually a 4 vector dot product, right? A 4 vector product, so I get a -1 actually, correct? So if you want, I'll indicate that with these indices. Okay, and then we are using the metric, this metric, so that's why I get a -1. Okay, that minus turns out to be important. Okay, what about the second term? I have again epsilon 1 is 0, 1, 0, 0, but epsilon bar 2 is 0, 0, something, something. So that's just a 0. Okay, so this is nothing but a -1. Okay, what about the other one, where I start with this helicity possibility for the E plus E minus going to mu plus mu minus. What about this? Obviously this is just epsilon 2, which I hit with both epsilon 1, epsilon bar 1, I'm sorry, and again an epsilon 2, which I hit with another epsilon bar 2 though. Okay, and again I'm going to write the Lorentz indices so that we do the contraction carefully. Okay, now what is this? What is epsilon 2? It's 0, 0, 1, 0. That means if I hit it with 0, 1, 0, 0, that's a 0. And if I hit it with this term, what does it pick out? It picks out a cos theta, but with a minus, again because of the metric. Correct? Good. So that's nothing but minus cos theta. Okay. Now we are going to put all of this together, because what we want at the end of the day is this, right? That's what gets into the cross section, and that is nothing but m1 plus m2 the whole squared, because amplitudes add up, right? It's worth expanding that. It is m1 squared plus m2 squared plus basically m1 m2 star plus m2 m1 star, right? Now we don't need to bother with these interference terms, because that just goes to 0. Okay, so why is that? Because the two helicity states that we're thinking about, these are helicity states at the end of the day, right? I can call them that now. The two helicity states, this state and this state that we are considering, right? These two don't interfere, right? So clearly that has to be 0. Okay. Okay, very good. So I only consider these two, and what is that now? That's just 1 plus literally cos square theta, right? That's it, right? So I have a 1 from this, so I have a minus 1 which is square. So sorry, earlier I said that minus turns out to be important, not so important here. And I have a minus cos theta, so I just square it and I literally get 1 plus cos square theta, right? Now let's go back to what the actual amplitude was. That was E square, we pulled out the coupling times this m tilde in terms of helicity states, right? So that just tells me that the actual m squared is e power 4 times 1 plus cos square theta, right? So in the m we pulled out an e squared, so in the m squared we have an e power 4. That's it. Okay, this is kind of all we want now. Okay, why? Because we have a general expression for d sigma over d omega in the center of momentum frame. Remember, right? So for center of momentum, I'm going to put Cm. Remember, we had a nice expression for that from all those lectures ago. So here you go, this one, right? And then we saw that if the masses are equal and all that, it simplified even further. I got this one, right? As long as the center of mass energy is greater than the final state mass, which is true in this case, we're taking them to be massless, in fact. I get this, right? So I'm just going to plug what we got now for m square into this formula and simply write for this process it is once again 64 pi squared ECM squared 1 plus cos square theta. Okay. Excellent. See, without much effort, without actually doing a QFT level calculation, using just helicity states, we were able to compute the cross section. Okay. Now, you might ask, what is the use of all this? Okay. The 0th order answer is that getting these differential cross sections is the very juice of knowing what's going on in the underlying theory. Okay, this is literally how you make predictions for what an experiment would see, right? Because these differential cross sections you can turn into differential events, and by counting events in this case in different angular angular distributions and various infinitesimal solid angles, that's literally how you actually test your prediction. Okay, that's a 0th order answer. In this case, there is actually a lot more that you can infer from this simple expression. Okay, this is historically has been one of the most important channels with which we understood a lot about the standard model. So we are going to see how. Okay, and to see that, I am going to ask, is the scattering here isotropic? This E plus E minus, do you think is isotropic? What does isotropic mean? It favors all directions equally, right? Is that true here though? Of course it is not, right? Why? Because I literally have this theta sitting here, right? I have a cos square theta sitting here. If I didn't have it, okay, so okay, I'm not able to close it with my hand, but if I didn't if cos theta term were absent, the cos square theta term, then yeah, sure, then this scattering cross section doesn't care about the direction. Remember, this omega actually has a cos theta sitting in it, right? So the fact that on the right hand side you have a cos theta or cos square theta biases this. Not all cos thetas are the same anymore, right? After all, the cross section is a measure of the probability of scattering in these directions for this particular case, right? So even more particularly, you know, if the scattering angle is either 0 degrees or 180 degrees, okay, these are more favored. What do we mean by that? This function 1 plus cos square theta as a function of theta gets to its maximum when theta is either 0 or 180 degrees, correct? If it's 0, cos theta is 1. If it's 180 degrees, cos theta is minus 1, but cos square is plus 1. So, you know, that's exactly where 1 plus cos square theta gets the maximum value, right? You can actually even plot this and see, right? So, if I take cos theta to be 90 degrees, that's when it vanishes, the cos theta vanishes, and the cross section is the least. Okay, so that means literally the scattering, the muons would like to go either in the forward direction or in the backward direction. Okay, is that clear? Let's look at this picture again. So the muons are scattering off in some random directions, but they would rather like to go, you know, either like this, or after scattering the muon would rather like to go like this. Okay, that is very close to the electron positron beam. Okay, you'll get a lot more events here than here. Okay, so that is what this is telling us, and that is something that can be very easily checked already, right? Okay, that is one thing. Another thing that you can infer is, notice that this is an even function of cos theta. Right? Or said differently, there is a, you know, if I take theta to 180 degrees minus theta, that will leave d sigma over d omega unchanged, right? What does that mean? How else can we say this? We can say that this process has mirror symmetry. Right? Or there's one more way to say this, which we've been saying since almost the first few lectures, which is that in QED, parity is conserved. We knew this, right? Even from Maxwell's equations, we saw that electromagnetism conserves parity, and we are finally seeing it in a particle physics collision process also. Right? So the fact that it's an even function of cos theta, and the fact that we put in only the photon, all of them are actually consistent with each other. okay, because if you have only the photon, this is a QED process, and so better to have parity conserved in the process, and that is what we are seeing. Okay. So, I am going to wrap up this lecture by saying that if you put in the Z boson also, okay, sorry, like this, if the same process is mediated by a Z boson, then you will see that parity is not conserved, okay, at the level of the cross section itself. Even in your d sigma over d omega, you are going to see this, and this turned out to be very historically important, and that is just what we are going to take up in the next lecture. So, I leave you here. Thank you. See you in the next lecture.